Assalamu alaikum and welcome to e-learning Al-Noor International School grade 11 chemistry course. I'm your chemistry teacher Fraz Anjum. Today we will start the lesson number 3, 19.3, which is strength of acids and bases. For this we have to refer the textbook page number 664 till 669. So please open your book, page number 664. This week our main objective is identify the property used to classify the acids and base as a strong or weak. So let us start. Strong and weak acid and bases. How are acid and bases classified as either strong or a weak? So answer is acids and bases are classified as strong or weak based on the degree of which they ionize in water. Means how much they're going to be ionized in the water. It depends their strength, that how strong and or how weak. In general, a strong acid is completely ionized in aqueous solution, such as hydrochloric acid and sulfuric acid are example of a strong acid. Look at here, HCl, when you pour into the water, it gives H3O positive, which is hydronium ion, and Cl negative completely. Means HCl breaks into H positive ion and Cl negative ion completely, 100% ionized. So that's why it's called strong acid. So the acid completely ionized is called strong acid, remember. And give the H positive ion, remember this one. Now, weak acid ionize only slightly in aqueous solution. The ionization of ethanoic acid, okay, a typical weak acid, is not complete. You can see here CH3COOH, okay. Ethanoic acid also called acetic acid, okay. When mixed in the water, it gives the only this hydrogen, okay. One means monoprotic, this one, because only one hydrogen it gives here. We discussed last week that why not this one is because of the organic or non-polar, okay. So I'm not going to explain again. So only this hydrogen going to be ionized, so it become H3O positive, and rest of the acetate ion remain like this. So less than 1% going to be ionized. So that's why it's called weak acid. So weak acid, what is it? A weak acid ionized only slightly in aqueous solution or not completely ionized. There are few uh, examples of acids, okay, which gonna be ionized, which one and which one not. Okay, look here. Hydrochloric acid, nitric acid, sulfuric acid. It's going to be ionized completely in the aqueous solution. That's why it's called strong acid. Okay, now phosphoric acid, ethanoic acid, and carbonic acid, hydrochlorous acid. You can see it's going to be increase the strength like this. Then neutral solution, which is acid, and then strong bases going decrease like this, ammonia, and then sodium silicate, then calcium hydroxide, then sodium hydroxide, then potassium hydroxide. Okay, so let us explain why all of this. Now you can see here the dissociation of the strong acid. So this is Ha, means H represent acid, A means anion. Okay, so a dissociated of acid Ha in water yields hydronium ion, because H give the H2O become H3O positive, which is hydronium ion, and anion A negative. The bar graph compare the extent of the dissociation of a weak acid and a strong acid. You can see here, these are the comparison. Now you can see this is the one acid, it completely dissociate and give the complete hydronium ion and complete anion, such as HCl going to be completely dissociated and give the hydronium ion completely, and then Cl ion here. And this is the equation for the strong acid. Now for weak acid, you can see in weak acid only few, very less than 1%, okay, going to be dissociate. The rest remains same, okay. So that's why we call this is weak acid. Now, strong acids such as hydrochloric acid completely dissociate in water. As a result, H3O positive is high in the aqueous solution for of strong acid, as I explained previous slide. By contrast, weak acid remain largely undissociated, which is this one. It remains same like this, okay. Only less than 1% going to be dissociate. So in an aqueous solution, the ethanoic acid less than 1% of molecule are ionized. So is incomplete ionization happened. That's why it's called weak acid. Okay, students. Now you can use the balance equation to write the equilibrium constant expression for the reaction. So what is equilibrium constant? Remember, in the previous lessons we discussed that equilibrium constant, normally we call Kc, is equal to the concentration of the product over the concentration of reactant. Okay, the concentration of product over concentration of the reactant is called equilibrium constant, which is Kc. Here we are using the equilibrium constant for this expression. Okay, now check here. You know this one, that ethanoic acid and water when mixed, it gives hydronium ion and acetate ion. Okay, how they dissociated. Okay, these equilibrium constant expression shown below is for the ethanoic acid. So compare this equation with the equilibrium constant. So Kc, instead of Kc we are writing here Keq. Keq means equilibrium constant. K represents for constant. Equal concentration of the product. So here how many products are here? 2, which is hydronium ion and acetate ion. So the concentration of hydronium ion times concentration of acetate ion over product. So what are the products here? Ethanoic acid and water. So the concentration of ethanoic acid times concentration of water. I hope you can understand. Okay, student, now let's take the example. Acid dissociation constant. For dilute aqueous solution, the concentration of water is a constant. Remember, always water is constant in dilute solution. This constant can be combined with the Keq to give an acid dissociation constant. So look here expression. In equilibrium, you wrote here times H2O concentration, but we took here and combined with equilibrium constant, okay, to give acid dissociation constant. Okay, so the combination of water in dilute aqueous solution with the equilibrium constant give the expression Ka, which is acid dissociation constant, and other expression remains same. So the acid dissociation constant Ka is the ratio of the concentration of dissociated form of an acid to the concentration of the undissociated form, which is this. Okay, so the dissociated form of include both the H hydronium ion and the anion. Okay, so the expression of Ka will be like this: the hydronium ion times acetate ion over ethanoic acid. Okay, this is how you're going to calculate the acid dissociation of ethanoic acid. So the dissociation constant Ka reflects the fraction of an acid that is ionized. For this reason, dissociation constants are sometimes called ionization constant as well. Okay, so means acid dissociation constant also called ionization constant. Okay, if the degree of dissociation or ionization of the acid is small, the value of the dissociation constant will be small. Okay, how? Check here. In weak acid, have a small Ka, which is acid dissociation constant value. Okay, if the degree of ionization of an acid is more complete, the value of Ka will be larger. In a strong acid, okay, the larger its Ka value will be. Okay, so means Ka value is small in weak acid and Ka value is larger in strong acid. So if you see after calculation Ka value is small, so compare with the other, so this one is supposed to be weak acid and the larger one become strong acid. Let's calculate it. Take this nitrous acid, which is HNO2, has a Ka acid dissociation constant of 4.4 times 10 power negative 4, but the ethanoic acid, which is CH3COOH, has a Ka of 1.8 times 10 power negative 5. So compare both and tell me which one is a strong acid and which one is a weak acid. So let's check. This means that the nitrous acid is more ionized in solution than the ethanoic acid. That's why nitrous acid is a strong acidic acid than the ethanoic acid, because nitrous acid has more or larger value. Look here, the power negative 4 and here negative 5. So negative 4 means is larger or bigger and is a smaller one. These are the few dissociation constant for weak acids. For oxalic acid, there are two. Okay, remember, because it's here two-step reaction. Okay, it's diprotic. Okay, phosphoric acid triprotic. So it has the two different acid dissociation constant, and it has the three different, means first step it gives you this, second step this, third step this. Okay, and then so on. You can see acid dissociation constant. Some acid have more than one dissociation constant because they have more than one ionizable hydrogen, as we just previously discussed. Oxalic acid is a diprotic acid. It lost two hydrogen, one at a time. Therefore, it has two dissociation constant. Oxalic acid is found naturally in the certain herb and vegetable. You can see here, this is oxalic acid. In oxalic acid, it has two because of the diprotic acid. Okay, so first hydrogen, when it lose, the acid dissociation constant value will be this at 25 degrees Celsius. From where we get? In the lab. Okay, and then when it's going to be dissociate the second hydrogen, it gives this value of Ka. So it means this constant, it depends on the acid, monoprotic, diprotic or triprotic. Okay, so observe what happened to the Ka with each ionization. The Ka decreases from first ionization energy to first ionization to second. Okay, it decreases again from the second ionization to third. Okay, compare here. You can see first is larger, second is smaller. Here first is larger, second is smaller, and then if you compare these two, means in the triprotic, so this one, second one is larger than the third one, so it's keep decreasing. To calculate the acid dissociation constant Ka of a weak acid, you need to know the initial molar concentration of the acid and the H positive ion, or alternatively the pH of the solution at equilibrium. You can use this data to find the equilibrium concentration of the acid and the ions. These values are then substituted into the expression of Ka. How? We can see here. So you can find the Ka of an acid in water by substituting the equilibrium concentration of the acid, which is AHA, and an ion from the dissociation of acid, which is A, and the hydrogen ion, which is H positive, into the equation. So what is it? Product over reactant. So what are the products? H positive ion concentration times anion concentration over the reactant, which is HA, the concentration of acid itself. And here we go, the expression Ka. So using this formula, we can calculate the acid dissociation constant. So calculate it. In 0.1000 molar solution of ethanoic acid, H positive ion concentration equal 1.34 times 10 power negative 3 molar. Calculate the Ka of this acid. Refer to the table of ionization equation for ethanoic acid. So what we note, that ethanoic acid, which is 0.100 molar, which is given in the question. Other one is H positive ion. Concentration is given 1.34 times 10 power negative 3 molar. What we need it, Ka, which is acid dissociation. So let's start. That start to determine the equilibrium concentration of the ions. So concentration of H positive ion equal the concentration of anion. Remember, okay, in completely has to be like this: CH3 COOH and H positive ion must be equal as a neutral compound. So what is the concentration of H positive ion? This is given same with the anion as well. So each molecule of CH3 COOH that ionize gives us H positive ion and a CH3 COO negative ion. Okay, remember this. The ratio is 1 to 1. Now determine the equilibrium concentration of each component. So 0.100 times minus 0.00134 molar give you 0.0987 molar. What is it? This is the concentration is given. Okay, so we get that 0.0987 molar, okay, is the concentration. So the concentration initially, what is the concentration of this, which is acetic acid or ethanoic acid? 0.100. What is the concentration initially, means before dissociation? 0. What is the concentration of acetate ion before dissociation? 0. After change, what happened? Okay, this one 1 minus 1.3 times 34 times 10 power negative 3. Why we are minusing here? Because this one is dissociated. It's given in the question. Okay, now when you minus it at equilibrium, what happened? We minus from 1 minus this, we will get 0.0987 at equilibrium. Okay, here remain same, here remain same, because 0 minus this same, 0 minus this same. Hopefully you understood this. Now using the Ka expression, you know this one. So Ka is equal to H positive ion times CH3 COO negative ion over CH3 COOH. This is the expression of acidic constant. Okay, now put the value. After putting the value, we will get this answer, and this is acidic dissociation constant. The calculated value K is consistent with that the weak acid. Just as there are strong acid and the weak acid, there are strong bases and weak bases as well. So a strong base dissociate completely into the metal ions and hydroxide ion in an aqueous solution. So remember, okay, completely ionized in metal ion and OH ion. A weak base reacts with water to form conjugate acid of the base and hydroxide ion. So for a weak base, the amount of dissociation is relatively small. Look here now. Ammonia is an example of weak base. Window cleaner often use a solution of ammonia in water to clean the glass. So ammonia with water give you ammonium ion and hydroxide ion. When equilibrium is established, only about 1% of ammonia is present as NH4 ion. This ion is the conjugate acid of NH3. Remember last week we discussed this. The concentration of H positive ion and OH negative ion are low and equal after this equilibrium. Okay, now put the equilibrium constant expression. Same here. K KEQ is equal to product over reactant. So what are the products? This one, ammonium ion concentration, OH ion concentration over product. Product is ammonia concentration and water concentration. Now same thing happen. You can see that water always constant. So we can remove the water and put here. So KEQ times H2O always said KB, which is equilibrium constant of the base or base dissociation constant. Okay, recall that the concentration of water is constant in dilute solution. Okay, as I explained just now. This constant can be combined with the KEQ for the ammonia to give the base dissociation constant KB for ammonia. Okay, now this is the expression for KB, and then after putting the concentration we can calculate the KB for ammonia. Now the base dissociation constant KB is the ratio of the concentration of conjugate acid times the concentration of the hydroxide ion to the concentration of the base. So KB is equal to conjugate acid, which is ammonium for the ammonia, times OH ion over complete base, which is NH3. The magnitude of KB indicate the ability of the weak acid to compete with the very strong OH negative or hydrogen ion. Because bases such as ammonia are weak relative to the hydroxide ion, the KB for such a base is usually small. So KB for ammonia is 1.8 times 10 power negative 5. So the smaller value of KB, the weaker the base. Okay, so a small value of KB, base will be weak. Sometimes people confuse the concept of the concentration and the strength. So what is concentration and what is strength? So the word concentrated or dilute indicate how much an acid or base is dissolved in solution. The amount of solute is concentration. If you remember, we discussed in the class. The amount of concentration, amount of solute is called concentration. So we can say the word concentrated dilute indicate the how much acid or base dissolved in solution. These terms to refer the number of moles of the acid and base in given volume. The word strong and weak refer to the extent of ionization, that how much going to be ionized, okay, or dissociate as an acid or base. For example, I'm just giving example here, you can understand easily now. See, if I take 1 mole of HCl and put into the 1 liter, okay, and after that I took 5 mole of water and put into the same 1 liter. So which one is the more concentrated? 5 moles HCl going to be more concentrated, and 1 moles HCl going to be, say, dilute. So how much we are going to put here? Same thing happened with the weak acid. Okay, that I take 1 ml of ethanoic acid and put here in the 1 liter of water, and same 1 mole if I'm taking the 5 moles of ethanoic acid, I'm going to take and put into the water 1 liter. So which one going to be concentrated, which one going to be called dilute? Definitely 5 moles of ethanoic acid called concentrated and 1 mole called dilute. It's not about the strong and weak, but the strong and weak acid is like a HCl is strong acid because it's completely ionized, and ethanoic acid is weak acid because it incomplete dissociate or ionize. That's it. Now the table below shows the possible combination and concentration of strength of acid. Look here, the acidic solution. Okay, so hydrochloric acid 12 molar HCl, relatively concentrated or strength is strong. Gastric juice 0.8 molar of HCl, which is dilute, and strength is strong. Why? Because HCl is strong acid. Okay, ethanoic acid 17 molar, which is concentrated, as I told you. Okay, and strength is weak. And vinegar 0.2 molar, which is dilute, but also called, this is weak acid. The gastric juice in your stomach is a dilute solution of HCl. The relatively small number of HCl molecules in a given volume of gastric juice are all dissociated into the ions. Even when concentrated hydrochloric acid is diluted with water, it is still a strong acid. Conversely, ethanoic acid, acetic acid, is a weak acid because it ionizes only slightly in solution. So vinegar is a dilute solution of ethanoic acid. Even the high concentration of ethanoic is called weak acid. This is the major difference of weak and strong and concentrated and dilute. The same concept applies to the base. A solution of ammonia can be either dilute or concentrated. However, in any solution of ammonia, the relative amount of ionization will be small. Thus, the ammonia in a weak base at any concentration. Likewise, sodium hydroxide is a strong base at any concentration. Checkpoint. In strong acid, are all ionizable hydrogen completely ionized? In weak acid, answer is in strong acid all ionizable hydrogen are completely ionized. In weak acid all ionizable hydrogen are partially ionized. And that's it for 19.3. Hopefully you understood. Any question you can ask in the comment, I can reply you. Thank you so much.